Hello friends, welcome to the channel. Today we will discuss a topic from PDE, which is classification of partial differential equation reduction to canonical forms. In, in the one of the previous video, I have solved a case question in which they have asked one question from PDE to reduce the given PDE to canonical form. So today I will discuss how to reduce a given PDE to canonical forms. So before that, we will see what is the classification of PDE of second order. So consider a general partial differential equation of second order for a function of two independent variables x and y in the form a of xy uxx plus b of xy uxy plus c of xy uyy plus h of xy ux uy equal to 0. So this is the general form of the second order PDE. Here a of xy, b of xy, c of xy are continuous functions possessing the partial derivatives in the domain. So let us denote the second order derivative uxs as r, uxy as s, uyy as t, and ux as p, uy equal to q. Then the given equation reduces a of xy reduces to a of xy equal to into r plus b of xy into s plus c of xy into t plus h of xy u p q equal to 0. So this is I will call as equation number 2. Now this equation is said to be hyperbolic at a point xy in domain D if b square minus 4ac greater than 0, parabolic if b square minus 4ac equal to 0, and it is elliptic if b square minus 4ac is less than 0. So the given PDE we have to write first in this form. Then here a the coefficient of uxs, b is coefficient of uxy, c is coefficient of uyy. If this b square minus 4ac is greater than 0, then the given equation is hyperbolic. If b square minus 4ac equal to 0, then the given equation is parabolic. If b square minus 4ac is less than 0, then the given equation is elliptic. Let us see some examples. So consider the one-dimensional wave equation given by uxx equal to uyy. So equation can be written as uxx minus uyy equal to 0. So here a equal to 1, b equal to 0, c equal to minus 1. Now b square minus 4ac you will get it as plus 4, which is greater than 0. Therefore the given given partial differential equation is hyperbolic. Now let us see another example. So consider another example, the one-dimensional diffusion equation. Consider one-dimensional diffusion equation. Delta square u by delta x square is equal to delta u by delta y. Okay, so this one equation 1 can be written as equation 1 can be written as uxx minus uy is equal to 0. So here a is equal to 1, b is equal to 0, c equal to 0. Now b square minus 4ac you will get 0 minus 4 into 1 into 0. So you will get it is 0. Hence the given equation b square minus 4 is equal to 0. Therefore the given equation is parabolic. Now consider another example. Consider two-dimensional Laplace equation. Consider two-dimensional Laplace equation delta square u by delta x square plus delta square u by delta y square equal to 0. So here a is equal to 1, b is equal to 0, c is equal to 1. Now b square minus 4ac is equal to 0 minus 4 into 1 into 1. You will get minus 4, which is less than 0. So the given equation is elliptic. Therefore, the given equation is elliptic. Okay, so we have seen some examples how we can check the given partial differential equation is hyperbolic, parabolic and an elliptic. Now let us see what is the working rule for reducing a hyperbolic equation to its canonical form. So let the given equation be given like this: a of xy zxx plus b of xy zxy plus c of xy zyy plus h of xy z pq equal to 0. Let this b equation be hyperbolic, then b square minus 4ac is greater than 0. So step 2, write the lambda quadratic equation, that is a lambda square plus b lambda plus c equal to 0. This is lambda quadratic equation. Let lambda 1, lambda 2 be its two distinct roots. Lambda 1, lambda 2 be its distinct roots. Step 3, the corresponding characteristic equations are dy by dx plus lambda 1 equal to 0 and dy by dx plus lambda 2 equal to 0. Here lambda 1, lambda 2 are distinct roots, so its characteristic equations are given like this. Solving these, we get f1 of xy equal to c1 and f2 of xy equal to c2. So I will call this is equation number 3. Next, step 4. We select u v such that u is equal to f1 of xy and v equal to f2 of xy. Step 5. Using the relations for u and v, we can find p, q, r, s and t in terms of u and v. Here p is zx, q is zy, r is zxx, s is zxy and t is zyy. So using the relation 4, we are finding the terms and substituting these values p, q, r, s, t in equation number 1. So equation number 1 is this. So we are finding zxx, zxy, zyy and p and q here in equation number 4. From this, after finding all the terms, we are substituting in equation number 1 and simplifying, we get the canonical form. Okay. So next, working rule for reducing the parabolic equation to its canonical form. So let the given equation be AR plus BS plus CT plus H of XY Z PQ. So given equation is parabolic. So B square minus 4AC will be 0. Now we have to write the lambda quadratic equation. It is same as in the case of hyperbolic. So lambda quadratic equation will be a lambda square plus b lambda plus c equal to 0. We get the roots lambda 1. It will be two equal roots. So lambda 1 comma lambda 1 be two equal roots of the lambda quadratic equation. Then the characteristic equation will be dy by dx plus lambda 1 equal to 0. So solving, we get f1 of xy equal to c1. Okay, next step 4. Let us choose u equal to f1 of xy and v equal to f2 of xy, where f2 of xy is an arbitrary function of x and y and is independent of f1 of xy. So for this, we have to verify the Jacobian of j of u. So here we are choosing f2 of xy such that it is independent of f1 of xy. So they are independent means their Jacobian of u and v should not equal to 0. So Jacobian is given like this. Next, using the u and v, we have to find the values of p, q, r, s and t in terms of u and v. Then after finding p, q, r, s and t, we have to substitute in equation number 1. Simplifying, we will get the canonical form. Okay. So these step 5 and step 6 are same in all the 3 cases. Next, working rule for reducing an elliptic equation to its canonical form. So step 1, the given general equation like this. It will be elliptic if b square minus 4ac is less than 0. The lambda quadratic equation is a lambda square plus b lambda plus c equal to 0. So b square minus 4ac is less than 0. It has lambda quadratic equation has complex roots. So lambda 1, lambda 2 be the 2 roots and they are complex conjugates. Next, the corresponding characteristic equations are dy by dx plus lambda 1 equal to 0 and dy by dx plus lambda 2 equal to 0. Solving these, we shall obtain the solutions of the form f1 of xy plus I into f2 of xy equal to c1 and f1 of xy minus I into f2 of xy equal to c2. So step 4, let us choose u equal to f1 of xy plus I into f2 of xy, v equal to f1 of xy minus I into f2 of xy. So let alpha and beta be two new real independent variables such that u is equal to alpha plus I beta and v equal to alpha minus I beta. So that alpha equal to f1 of xy and beta equal to f2 of xy. Now the step 5 and 6 are same as in the cases of hyperbolic and parabolic equations. That is, in case step 5 we have to find the p, q, r, s, t using these equations alpha and beta. Then you have to resubstitute that in equation number 1, the general form of the second order PDE. And after simplifying, you will get the canonical form. So let us see some examples in the next video.